Good day. My name is Jeff Major, and I am the Global Product and Service Line Director for Inspection Services at Team Incorporated. This talk describes Team's integrated touchpoint corrosion solution. Before I present the characteristics of Team's touchpoint corrosion solution, let's first understand what touchpoint corrosion is and what challenges it brings to the industry. Many processing facilities, such as refineries, experience leaks and/or failures in their piping systems due to touchpoint corrosion. This results in a significant environmental and financial impact. In some cases, facilities do not know they have an issue until it's too late. In severe cases, units must be brought down prematurely to remediate the touchpoint corrosion issue. So what is touchpoint corrosion and what are the challenges? Touchpoint corrosion, also known as corrosion under pipe supports, is a non-uniform damage mechanism that occurs at the interface of the piping system and support. The support can be metallic or non-metallic, and in some cases can be unintentional, such as a pipe resting on another pipe. The image on the slide shows an example of touchpoint corrosion that can be seen visually. This is not always the case, though. Touchpoint corrosion at these highly localized points presents particular challenges as the damage is difficult to avoid, difficult to detect, difficult to measure, and difficult to remediate. Team has evaluated these four challenges and has developed an integrated touchpoint program that offers a turnkey solution to address the detection, measurement, and remediation. The program flows from screening to evaluation to engineering assessment to engineered line lifting to remediation and finally continued monitoring. Now that we have a very basic understanding of touchpoint corrosion and its challenges, let's discuss what the aspects of Team's touchpoint corrosion solution look like. A typical facility will have anywhere from 100 to tens of thousands of touch points. Although all touch points are critical to some extent, some are more critical than others. Having the ability to screen touch points for severity provides the client with a cost-effective technique to prioritize assessments, resulting in significant cost savings. We have three primary techniques to screen and catalog touch points. The first technique is laser scanning, which offers a quick and reliable technique to create three-dimensional models of the plant, facility, or unit. The geospatial data allows touch points to be identified, digitally tagged, and cataloged. The 3D models can also be used for identifying access constraints and inspection locations. The second technique is the deployment of drone and robotics, either in parallel to the 3D laser scanning or independently. Drone and robotics offer an advantage when visual inspection of touch points is required in access-restricted areas. The third technique is visual inspection or confirmation of damage severity utilizing our staff of fully certified rope technicians. Rope technicians can be deployed in parallel to the other two techniques or independently. In addition, rope technicians can deploy a number of inspection techniques for evaluation without the need for scaffolding. Now that we have cataloged and ranked the touch points, we need to evaluate them to determine their severity. Team has a range of NDE techniques that allows our subject matter experts to determine the severity of damage. Initial deployment of NDE consists of indirect screening tools. As the name suggests, these are qualitative assessments that provide a description of the damage, or in other words, a go-no-go screening. Probably the most popular technique deployed at the initial onset of touchpoint corrosion evaluation outside of visual inspection is guided wave testing. Guided wave can be used on a significant range of pipe diameters. However, its most popular feature is its ability to evaluate multiple touch points on a straight run of piping from a single location. When guided wave is not practical, for example, short runs on multiple branch connections, mid-range or bulk wave ultrasonics is typically the second choice. Assessment can be achieved at an axial range of 36 inches or less. It provides similar results to guided wave, but requires the operator to be at each touchpoint location. If a more critical damage assessment is required, based on guided wave or bulk wave inspection, electromagnetic acoustic testing is typically the next selection. EMAT, not to be confused with eddy current, is another indirect ultrasonic screening tool that gets us closer to quantitative assessments. However, signal processing is more complicated and configuration limitations make this a supplemental technique. One caveat to the EMAT technique is the quantitative short-range system that allows for true quantitative results based on the system's proprietary signal processing. However, it is a true circumferential inspection that requires a system to be directly above the touch point. Thus, access restrictions or fasteners, for example, U-bolts, have to be taken into consideration as well as pipe diameter. Another technique that provides good data and sizing is profile radiography, but access has to be ideal to deploy the technology. All of the techniques described are indirect measurements. Additional techniques that we would deploy if we were allowed to lift the pipe would include pit depth measurements, ultrasonic thickness with pencil probes, and laser scanning. Although we discussed the typical NDE techniques that would be deployed to assess the touchpoint corrosion damage, every project is unique and requires an evaluation of the appropriate set of NDE tools to be deployed. Once we identify that an issue exists that needs to be addressed, we need to deploy an engineering assessment. Although engineering assessments contain many parts, we can summarize them into three categories. First, we need to conduct a fitness for service to ensure that a lift would not result in a leak event. For example, is the remaining material strong enough to support the load from internal pressure and any potential bending? Second, we need to conduct a pipe stress analysis for lifting. The stress analysis should be done in conjunction with